All right, let's just jump right in. Welcome to this explainer, where we're embarking on a comprehensive chemical survey of typical proton NMR absorptions. If you've ever stared at a wildly complex spectrum and struggled to quickly parse through the noise, you are definitely not alone. It can be overwhelming. But today, we're going to transform all that raw data into a beautifully structured, highly predictable map. So how exactly do we figure out the intricate blueprint of a completely invisible compound? The answer, of course, lies in the molecular fingerprints of NMR spectroscopy. Nuclear magnetic resonance is, let's face it, arguably the most important spectroscopic method we have as organic chemists. While other tools might hint at what functional groups are hanging around, NMR gives us the exact number of magnetically distinct hydrogens and just incredibly detailed clues about their immediate neighborhood. It is literally how we map the invisible, atom by atom. To keep from getting totally lost in a sea of data, here is our roadmap. First, we'll quickly decode the molecular fingerprint. Then, we're treating the NMR spectrum like a topographical map, traveling from the upfield shielded hydrocarbons into the midfield electronegative shifts, through the downfield double bonds and rings, and finally, landing at the extreme territory of carbonyl compounds.
Okay, step 1, decoding the molecular fingerprint. Let's just briefly recap the basic mechanics of how this mapping tool actually works.
It all boils down to spin. Protons possess a quantized spin of 1/2, meaning they act a lot like tiny little bar magnets. And when you drop them into a strong applied magnetic field, they really just face a choice: relax and align with that field for a nice, lower energy state, or fight against it in an opposed orientation for a much higher energy state. Think of it like a set of ordinary bar magnets. That aligned configuration is super stable, right? Very low energy. But in the opposed arrangement, the center magnet is essentially repelled out of its high energy state. When a nucleus absorbs the exact right amount of radiofrequency energy, it actually flips from that stable aligned state to the opposed state. And that resonance, that flip, is exactly what generates our measurable signal. Moving right along to section 2, let's start our map journey upfield with the shielded hydrocarbons. So we're starting out in the safe, highly shielded suburbs of the spectrum, between 0 and about 2.7 parts per million. In this upfield zone, simple hydrocarbons like alkanes and alkynes reside incredibly comfortably under a thick, protective blanket of electron density. That blanket shields them from the machine's magnetic pull. Because they're so well shielded, it takes less of an applied magnetic field to cause resonance, keeping their chemical shifts nice and low. For your saturated alkanes, all those CH absorptions typically cluster between 0.7 and 1.7 ppm. Terminal alkynes also pop up here, around 1.7 to 2.7 ppm, because their acetylenic hydrogen is uniquely shielded by the anisotropic field of those adjacent pi bonds. Take octane, for instance. What's really interesting here is just how tightly clustered those peaks are on the far right. In long hydrocarbon chains like this, the methylene protons often overlap into a big, unresolvable group. But check out that tall, sharp peak furthest to the right. The most shielded protons of all are those methyl groups right at the ends of the chain. They show up at even lower chemical shifts, around 0.7 to 1.3 ppm, and they stand out super clearly from the rest of the chain. All right, leaving the suburbs behind, we enter section 3, the midfield and the electronegative shift. So between roughly 2 and 5 ppm, we encounter some fairly severe magnetic weather. This is where we see the powerful effects of electronegative atoms. Elements like oxygen, nitrogen, and halogens, they act like absolute electron thieves. They rip electron density away from neighboring hydrogens. Remember that protective electron blanket we just talked about? Gone, stripped away. And without that shielding, the protons feel the full brunt of the applied magnetic field, shifting their resonance signals downfield, towards the left. The exact shift depends on electronegativity and distance, but it always moves the signal the exact same way, downfield. You can see this perfectly with 1-chlorobutane. Notice how the protons directly attached to the exact same carbon as the electronegative chlorine atom are significantly de-shielded. They get pushed visibly downfield to the left, sitting right near 3.5 ppm. But, the effect totally diminishes with distance. So the protons further down the butane chain march systematically right back toward that shielded upfield right side. It creates this beautiful step-by-step visual of electronegativity at work. Now we're crossing over into the wilderness, section 4, downfield territory, dealing with double bonds and rings. Okay, if you take nothing else away, remember this. The 6.5 to 8.0 ppm range is a massive, massive clue. When you're surveying a chemical structure, this numerical range is essentially VIP parking reserved almost exclusively for highly deshielded hydrogens attached to aromatic rings. Seriously, very few other types of hydrogens ever show up in this territory. So, if you see a cluster of peaks here, you can almost guarantee a benzene ring is part of your unknown molecule. So why are they pushed so incredibly far left? It's all about the ring current. The aromatic ring generates a huge anisotropic field because of the continuous circulation of its pi electrons. That circulation actually creates an induced magnetic field that completely aligns with the applied field right where the protons are sitting, exposing them to some really intense magnetic forces. Check out this effect in alpha-chloro-p-xylene. See those sharp peaks isolated on the far left side, totally separate from the aliphatic protons on the right? Those are your highly deshielded ring protons. Now, alkenes also claim some of this downfield real estate. Protons directly attached to a double bond, or vinyl protons, generally absorb somewhere between 4.5 and 6.5 ppm. Similar to the aromatic rings, this is totally due to the diamagnetic anisotropy of the carbon-carbon double bond's pi electrons. Look at 2-methyl-1-pentene. You see that distinct peak cluster hanging out right around 4.7 ppm? Those are your deshielded vinyl hydrogens, standing totally apart from the shielded upfield signals of the alkyl chain. Finally, Section 5. We reach the absolute extreme edges of our map, the carbonyl compounds. Here's where the heavy hitters live, and they build a really complex picture. All hydrogens adjacent to a carbonyl group, the alpha hydrogens, absorb in a remarkably tight cluster around the 2.1 to 2.5 ppm range. That's because of the deshielding anisotropic field of the carbon-oxygen double bond. So ketones, aldehydes, esters, amides, carboxylic acids, they all actually share this feature. But the rest of the molecule creates wildly different extreme chemical shifts depending on the specific functional group, and that is exactly how we tell them all apart. Just compare a ketone to an ester. It brilliantly highlights this difference. Both of them have signals in that 2.1 to 2.5 ppm alpha hydrogen sweet spot. But look at the ester. It has an extra peak pushed all the way downfield to the 3.5 to 4.8 ppm range. Why? Because those specific hydrogens are sitting on a carbon attached directly to the ester's heavily deshielding single-bonded oxygen atom. It's a total dead giveaway for an ester. And finally, the absolute extreme edge of our map, reaching way up to 11.0 to 12.0 ppm. This is the nearly exclusive domain of the intensely deshielded carboxylic acid proton. Almost no other common type of hydrogen ever appears this far downfield. Now, because of hydrogen bonding and rapid proton exchange, this peak can often be super broad. Sometimes it even looks like it's melting into the baseline. But if you spot a signal way out here at the edge of the wilderness, congratulations, you found a carboxylic acid. So, we've traversed the whole landscape together, from the safe upfield suburbs of alkanes, through the midfield electronegative shifts, across the downfield aromatics, and out to the extreme frontiers of the carbonyls. You don't just have a list of numbers anymore. You possess a geographic map of electron density. So I have to ask, the next time you're faced with an entirely unknown compound, which territory are you going to look at first to crack the code?